Hello pre-calculus students, and welcome to our lesson on derivatives. And this is a very brief introduction, but we will get into some of the nitty-gritty details of the derivative here. So before we get to the derivative and what that really means, let's just start with this problem. Given f of x equals 2x squared minus x minus 1, find the instantaneous rate of change for x equals 3. So first thing that I'm going to do here, and actually for x equals 3, x equals 5, x equals 15, and so on. So I'm going to deal with this one first. So I'll start with a little bit of a graph. Let's see, when x is 0, f of x is negative 1. And then, of course, the vertex here, and I know this has been a while, is negative b over 2a. So this is 1 over 4. So once we figure that all out, the vertex is about here. It's very close to this, and it's going to look roughly like that. Okay, this is going to be a parabola, so nothing really special about this. But when x equals 3, so when x equals 3, f of x is, or f of 3 is some number right here. And we want to look for the instantaneous rate of change. In other words, we're looking for the slope of the tangent line. Okay, so this is a tangent line. And this is not the same definition as the tangent line, as the tangent in trigonometry. Okay, so it's a line that touches a curve at exactly one point. And we're looking for the slope of that when f equals 3. Okay. So we apply with the definitions that we've worked with before. And a quick caveat is that, I've made some other videos that introduces derivatives. So if you aren't familiar with this yet, you should check out some of those videos or ask your teacher for further help and explanation. And really, you really kind of need a person to explain this to you and walk you through it, because these are not easy concepts. Okay, so for x equals 3, this is the limit. So it's of some generic point x. So let's say this point here is x, and this is f of x. So it's the limit as x approaches 3 of f of 3 minus f of x divided by 3 minus x. In other words, I want to take this point here, and so this is initially the estimate, it's some line right here, but I want to take this point here and move it closer and closer and closer until it reaches this point. And that's what this limit is telling me. I'm going to move x until it gets close to 3. So I can't make the substitution yet because it is going to lead me to division by 0. So this is equal to the limit as x approaches 3. Substitute 3 in here and you get, let's see, 3 squared is 9, that's 18, minus 3, that's 15, minus 1, so that's 14. Minus, so let me do this the right way here. 3 squared minus 3 minus 1. So that's the specific value of 3, and then minus the generic value, 2x squared minus x, minus 1. All of this over 3 minus x. We'll continue this over here, equals the limit as x approaches 3. This is 9, 18 minus 3 is 15, minus 1 is 14. Distribute this negative sign here, and we get 14 minus 2x squared plus x plus 1. All of it over 3 minus x, and that's equal to the limit as x approaches 3. 14 and 1 here give you 15. All of it over 3 minus x. And again, you see this is really just algebra from this point on. I'm going to factor out a negative 1 on the top, so this is 2x squared minus x minus 15. Factor out a negative 1 on the bottom, so we get x minus 3. The negative 1's go away completely. And now I'm going to factor the top one more time. This factors to 2x plus 5 and x minus 3. So These terms cancel. And the nice thing about this, now that it cancels, I can do direct substitution. So this is 2 times 3 plus 5, which is 11. Whew, that was tough. Okay. So we got the answer for this part. Let's continue here and get the answer for when x equals 5. And I'm going to go through this quite quick just because it's very tedious. And if you have a hard time, feel free to rewind it and hit pause. So now we're going to do this for x equals 5. So this is the limit as x approaches 5 of f of 5 minus f of x divided by 5 minus x. So this all here is equal to the limit as x approaches 5. And if I substitute 5 in here, I'm just going to do this without the extra work just to save us a little bit of time. So this is 25 times 2, that's 50, minus 5, 45, minus 1, 44, minus 2x squared minus x minus 1. And you just got to be careful to put parentheses around this big term right here. I can't tell you how many of my students over the years have just forgotten that and totally messed up the problem. So this is equal to the limit as x approaches 5. This is 44 minus 2x squared plus x plus 1, distributing the negative sign. Okay. Continue over here. This is the limit as x approaches 5. 44 and 1 gives you 45 over 5 minus x, and that's equal to the limit as x approaches 5. Factor out a negative 1. Factor out a negative 1 in the bottom. And then just continue our work here. And again, I am going pretty quick because most of this is algebra. So factoring the top, you're going to get 2x, x minus 5, x plus 9 over x minus 5. That cancels. And now we can do direct substitution. 2 times 5 plus 9, and your answer should be 19. Okay. Another tedious process. And we could continue on the same way with 15 and 37, but this is going to get quite complicated. All right. So now my solution here is so I want to make a note here. This process is repetitive and tedious. So we need a better way. Now, the better way that I'm going to propose and present to you here is quite challenging, okay? Because this is always the trade-off. If you want to do something that makes life simpler, you have to do the work for it at least once, and it might be more challenging, but the reward is that you kind of get rid of all the tediousness. So I am going to add a layer, what I call a layer of abstraction. Make the problem more abstract. Okay? Make a more abstract problem. And abstract can sometimes seems like it's a negative word, but it actually helps us to make our lives a little bit easier. So instead of using x equals 15, x equals 5, x equals 3, I'm going to say x equals a. So I'm going to say this point here is a. This point here is a. Okay. All right. So essentially what I'm doing is finding the limit as x approaches a of f of a minus f of x over a minus x. Now I'm going to add another layer of abstraction here, and we can see here from the graph that a is actually greater than x, and that the distance between x and a, we'll call that h. So h is the distance between a and x. So in other words, a is equal to x plus h. X plus the distance h equals a. And then I can do a little bit of algebra here. A minus x equals h. And really these two things are saying the same. Now, as x approaches a, in other words, as we move this point x closer and closer to a, h gets closer to 0. As x gets closer to a, h gets closer to 0. That's like saying as x and a get closer to each other, the distance between them goes to 0. So I know it seems a little wacky and unusual that I'm doing this, but it is going to help us in the long run make things a little bit better. And I'm going to use a new board here. So this is going to take a little bit of space. So I am going to rewrite everything using h instead of a. So now I'm going to say, instead of the limit as x approaches a, I'm going to say the limit as h approaches 0, because those are the same thing. And instead of saying f of a, well, a is just x plus h, so f of x plus h minus f of x over a minus x, which is really just h. Okay. This right here is, we pronounce this f prime of x, and in the mathematical community, this is defined as the derivative. This is a derivative. And it is a function. Okay? Don't forget this. This is a function, okay? Not a number. So the beauty of this is that we're going to do this whole process here, and we're going to get a function, and then we can reuse that function again and again and again and again. Okay, so we're going to apply the definition of f prime, or the derivative, to our example. So I take the limit as h approaches 0 of f of x plus h, but don't forget that f of x is just 2x squared minus x minus 1, so this is 2 times x plus h squared minus x plus h quantity minus 1 minus f of x, so minus 2x squared minus x minus 1, all of it over h. Okay, now this is going to get quite complicated, but that's okay, because again, this is tedious, but the beauty of having an abstract solution is that it only has to be tedious once. So now this becomes the limit, and this is pure algebra at this point. This part here is just 2 times x squared plus 2xh plus h squared minus x plus, I'm going to distribute this negative sign here. I'll use a different color to make life slightly easier. So we're going to distribute this negative sign here, minus x minus h minus 1. Then I will distribute this negative sign, minus 2x squared plus x plus 1. All of this is being divided by h. Distribute the 2. Distribute this 2 here. And now we get the limit as h approaches 0 of 2x squared plus 4xh plus 2h squared minus x minus h minus 1 minus 2x squared plus x plus 1. All of it over h. And here comes the fun part, is when we get to cancel stuff. So negative 1 and positive 1 cancel. Negative x and positive x also cancel. 2x squared here, use a different color, 2x squared here and negative 2x squared cancel. And what are we left with? Well, a much simpler expression, the limit as h approaches 0 of 4xh plus 2h squared minus h, all of it over h. Now again, we still can't make this direct substitution yet, so we'll just factor out an h. So this is the limit as h approaches 0 of h times 4x plus 2h minus 1. All of this over h. So these h's cancel. And now we can make the direct substitution. I'll use a different color here just to mix it up a little bit. So this is 4x plus 2 times 0 minus 1, which is 4x minus 1, which is equal to f prime of x. Whew. So there you have it. If you take the derivative of this function that we were given here from the very beginning, this is what you end up with. This got smeared a little bit here. So now becomes the question is, what is this good for? What is this function good for? Well, remember our original problem, the instantaneous rate right here for x equals 3, x equals 5, x equals 15. So let's try this. I'm going to rewrite this here. So remember f prime here is equal to 4x minus 1. Well, f prime of 3 is equal to 4 times 3 minus 1, which is 11. Go ahead and rewind the video and confirm that this is the exact value that we got before. F prime of 5 is 4x, or 4 times 5 in this case, minus 1, which is 19, which is the exact same value that we got last time when we use this. And now we don't have to use the limit definition for this point anymore. We can just use f prime of 15. Just 4 times 15 minus 1, and that's 59. F prime of 37 is equal to 4 times 37 minus 1. A considerably easier problem to do. This is 120 plus 28, so 148 plus 28, I'm sorry, which is 148, minus 1, 147. So once we are able to derive this equation for the derivative, we can just repeatedly use it again and again for each one of these values. Now this derivative is different for every single function. So when you get a different function, you have to do this long tedious process down here again, okay? But it is very useful if you just really need to know a bunch of different instantaneous rates of change. Well, thank you for watching. I know this is a big leap for many of you, but I assure you, if you can understand the basic concept of what instantaneous rate of change means, and you're strong with your algebra skills, you will do just fine. Keep working at this. Keep asking for help if you need it. Thank you for watching. Have a wonderful day.